right, look at that, 5 o'clock. I'm gonna put this in now because I think that's gonna mess up my internet. If
I don't know.
And can you send Brandon that?
I got it on my phone. I did not get it.
Oh.
Is it showing that we're...
I'm live, but I have no one else on. This?
Or the one behind it.
What do you want me to do? Like more?
Okay, I can.
Yeah? Those invitations in. Hello. And Dane.
Yep.
I can start touching things. Okay.
You want to just say something, make sure our audio's fine?
Sure. We're getting things just finally set up here for the 3rd office hour of Alien Worlds, and we will we just posted the links, and hopefully people will be joining us soon, and we will be starting here shortly. Are you in, Brandon?
Yeah.
I'm not sure that you're just in Google or maybe that.
My internet's a little iffy, so I assume it's a good thing you have speed.
Yeah. Yeah, let's start. You don't need to be logged in. You need the Google thing.
Right.
Oh, that's fine. I don't see it. I just see you within. All right.
It's fine. That's all I'm saying.
Okay.
Mine shows me in there, just not her.
Weird.
Who knows?
Okay.
Paul H.C. says, given that an M-dwarf star has a potential lifespan greater than that of the universe, what impact would that have on a habitable zone? Will a tidally locked Goldilocks exoplanet or a star as a formality or a habitable?
Wow. Holy mackerel. So we have a really long question that I'm going to try to repeat as best I can that Brandon just told me. And that is, given if we have M-dwarfs that last essentially forever. I mean, they have main sequence lifetimes that last from hundreds of billions of years to literally trillions of years. And if you imagine that you had a habitable world orbiting an M-dwarf, especially a late-type M-dwarf, or maybe, a really the coldest of the coldest M-dwarfs, and you actually had that the the planet is so close that it's what's called tidally locked, which means the same face of that planet is always facing the star. That's similar to what the moon is around the Earth. We always see the same side of the moon because it's tidally locked. The tides from the Earth are so strong that it doesn't actually let the moon rotate. The same thing is true if you had a planet really close to a star. It wouldn't actually be allowed to rotate. So the question was, if you had this situation, if you had a very long-lived star and a tidally locked planet living in the habitable zone, because remember, for a cooler star, the habitable zone, the place you could have liquid water on the surface, is going to be much closer to that star. Would that planet essentially be habitable forever? And the answer is yes and no. Yes, in the sense that it would have probably the right temperature. It likely could even have potentially liquid water on the surface for, hundreds of billions, if not trillions of years. But the reality is that there's other things that make a planet probably habitable. One of those things that we didn't talk a lot about in this course is the geologic activity of a planet. It's something we think is really important to having Earth have the conditions that it has. The fact that we still have radioactive material in our core and mantle helps keep the inside of Earth warm. It's what keeps the Earth having plate tectonics, which actually maintains our carbon cycle, which does a variety of other things. It's what helps keep us have an active magnetic field. And that's really important, we think, to protecting the Earth from some of the high energy particles coming from the sun. That typically is a function of how large a world is, how long a world stays geologically active. So for smaller terrestrial worlds, they run out of that geologic activity relatively quickly. Worlds like Mars in our own solar system is no longer geologically active, although it once was. Earth and Venus still are, but they won't be forever. So the answer is, you would have the such conditions that you'd have, the right temperature for liquid water on the surface for hundreds of billions or trillions of years, but you would not have geologic activity. If that probably only lasts, depending on the size of the world, maybe as long as a few tens of billions of years. Long answer to long question. Sound good? Good. All right, next question.
Okay. Is it possible for light to orbit anything?
Oh, question is it possible for light to orbit anything? Um, I guess the answer is yes. Light doesn't have mass, and so it doesn't feel the force of gravity the way something like a planet does. And yet, um, light responds to the bending of space. So we talked about a little bit when we talked about how gravity works, that it actually is bending space. It's actually bending time too a little bit. And then that bending of space, if you shone a light through a really bent part of space, the light will actually travel in a curve just like space does. And we actually see that when we look into the especially distant universe. We can actually look behind large clusters of galaxies is a good example. And you can actually see light that is on the far side of those galaxies being bent around the clusters of the galaxies because the cluster has so much mass, it's really bending space a lot. So, it's not that light is responding to gravity in a way of us feeling a gravitational force, but it is traveling through the curved space created by gravity.
Okay. Is it possible for two stars to orbit in the same system?
Oh, is it possible for two stars to orbit the same system? I guess the simple answer is yes. I mean, I'll answer that in a couple different ways, but certainly it's true that there are many binary stars in the night sky. In fact, most of the stars, at least like our sun and more massive, are binary stars, or at least half. When you go down to the lowest mass stars, which of course are the most common, the binary frequency or the number of stars or percentage of stars that are in these binary systems is actually much lower. But certainly, yeah, we see lots of binary stars in the universe. If the question is more specifically concerning planetary systems, we do now know some planetary systems that have two stars in the center. So they have a binary star, and then planets are orbiting them. We now know of some binary systems where you have two separate stars, and there are planets around the wide stars. So yes, in kind of all of those cases, we have multiple stars, and you can have planetary systems in multiple star systems as well.
Okay, so then there's an addendum to that. Can two binary star pairs orbit each other?
Oh, yeah. So the question is, can you have two binary star pairs orbit each other? And the answer is also yes. We call those quads or quadruple systems. And it is also that's a very common and stable configuration if you have two very close pairs, binary pairs. So you have, if my tips of my fingers are each a star, so there's two stars over on my left side and two stars here over on my right side, and they're separated by some distance that kind of orbit each other like this, and then these are orbiting each other like this. That is actually a stable configuration, and we see systems like that. I actually, in my research, have studied a lot of systems that look like this, or triple systems, where you have one star over here, and you have two stars that are very close over here that are in a mutual orbit with this other star, like that. That's actually extremely common, it turns out, for a variety of reasons.
Okay, I don't know how well you would do this, but somebody wants to comment on an article in Science about magnetic field calculation for types of planets.
Oh, there's one of the questions on the forum is asking me to comment on a new science article on magnetic fields on exoplanets. Do you have the article, Brandon?
No,
is it the inferred?
They inferred it based on measuring the line.
Yeah. So I did actually see this paper. So this is it's actually it's a fairly recent paper, if I remember. It's by a Russian group. Yeah, if I remember. So I did see this paper. The question is asking me to comment on a recent paper in the journal Science that is actually examining the magnetic fields on planets, which we haven't really detected yet. It's a very hard measurement, other than planets in our own solar system, but it's a very hard measurement to make of the magnetic field on a distant exoplanet. But this is a technique that they use to infer that based on basically the inferred size of the atmosphere that gets changed by when you have magnetic fields present on the planet. And of course, as the size of the atmosphere changes, turns out the detailed shape of the transit curve actually changes a little bit. So this is a kind of clever way that you can use different wavelengths of light to actually probe the atmosphere of exoplanets by looking at the detailed shape of the transit curve. And this is what this group found is they found differences when they looked at different wavelengths of light, and they inferred that the different shapes of this, or the different sizes of this planet's supposed atmosphere, were caused by magnetic fields. So it's a very clever way of trying to do this. Now, we don't know if exactly that, if that is exactly what they're seeing, but it's a pretty good notion that that's maybe what they're seeing. And someday we will have the ability to directly measure magnetic fields on exoplanets. It just hasn't been done yet.
Okay. Will a planet's rings show up in transit?
Oh, that's a neat question. So someone asked, will a planet's rings show up on a transit? Well, presumably they could, just like a planet's moons could show up in transit, if you think about that, right? If you had a moon passing in front of your planet, it would dip, down the light, or pass in front of the star. It would dip the starlight by just a little bit more. Same thing's true of a ring system. A ring system is, basically a bunch of ice and rocks that will block a little bit of the light. Now, many of the ring systems in our own solar system are actually pretty transparent, or at least they have some opacity. So they block, and by that I mean they block some amount of light, but some light gets through. And so even Saturn, which has the most impressive ring systems, would let a little bit of light through, but some of the light it would block. Now it's just blocking a tiny bit of the light if that were going in front of this star. And so in theory, you certainly could block light with the rings. I don't think that has been seen in reality yet, but again, we also haven't detected exomoons, but we assume that, so if you look at the abundance of satellites or moons in our own solar system, it would be silly to think that all these other exoplanets that we've been finding around other stars don't have moons. And so at some point we will be able to do that, but our technology just isn't good enough to detect transit signals that are that faint. So we can detect, just about Earth-sized worlds, but around solar-type stars, that's about the level we can do. But we can't do a whole lot better than that.
Okay. This question here admits it's kind of out there, but first off, what is antimatter, and what happens if you throw antimatter into a black hole?
Whoa. So the question is, what is antimatter? And then there's a second part to the question, what happens if you throw antimatter into a black hole? So the first one I think I can answer. The second one I'm not so sure I can. But the first one is, what is antimatter? And it turns out that antimatter, there are really two types of matter in the universe. There's the normal matter, like you and I are made up of, things like protons, electrons, those would be like normal matter particles. And then there are antiparticles. These are particles that are kind of opposite to those kind of normal matter protons. And we could get into a whole particle physics discussion about what all the differences are. When those two meet, when you combine matter with its antimatter counterpart, they do what's called annihilate. They turn into pure energy. And it's something that is one of the kind of balancing laws of nature, And one of actually the problems in some of our current notions of physics is that, you would think in a perfect symmetric world, we would have, just all as much antimatter as we would have matter, and that's problematic because if you have, giant antimatter galaxies and antimatter stars, and they all of a sudden collided with matter galaxies and matter stars, you'd have these giant annihilation events. And it doesn't appear that we have it. It appears that there is an overabundance of normal matter, which is pretty good for us. If you took antimatter and you put it in a black hole, I'm not actually sure what happened. I mean, a black hole still has mass, which is made up of real matter, and so there would be some kind of, I guess, internal annihilation. Of course, we would never see that because once it crosses the event horizon of a black hole, which is the point of no return, nothing gets out. And that includes matter or antimatter or any of the energy that would be produced in an annihilation event. So I think what would happen if you put antimatter into a black hole, the black hole would just get more massive, right? Because essentially the antimatter particles would go into the black hole. They would do whatever they're going to do, which could include annihilating with matter particles. But not even the energy or light that's produced, once it gets past the event horizon, can get back out. So I think you just have a more massive black hole. Do you guys concur? Sure. Yeah. I don't know the exact answer to that, to be totally honest, but that makes sense to me.
Given a lifespan of trillions of years, which exceeds the thickness of the universe, does a red M dwarf star represent perpetual motion?
Ooh.
I think what they're trying to get at is that effectively the energy that what the classifier is.
So it's an interesting question. So question is, if, again, it's going back to the fact that the lifespan of a really low mass star, an M dwarf, can exceed literally 1 trillion years with a T, trillion. So that's 10 to the 12 years. And that is, vastly longer than even the current age of the universe, which is, 14 billion years old, roughly, give or take some. And so the question is, does that system then represent perpetual motion? Is that essentially like all of the energy going on forever? Well, the answer is really no. I mean, trillions of years is a long, long time. I mean, that's the universe, being, as old as it is now, many, many times over and over again, right? But it's not infinite. There still will be a time, sometime in the long distant future, when an even low mass star will run out of gas. And we think many of these stars still will go through a red giant phase. They will blow off their outer envelopes, just like a star like our sun would. But again, we've not observed any of these stars do that because even the most massive M dwarfs still last hundreds of billions of years, which is longer than the current age of the universe. But eventually, they will all die. There is no perpetual motion, even for low mass stars.
How can we actually determine the mass of a star or
Ooh. How can we actually determine the mass of a planet, a star, or an exoplanet? Okay, so both of those are using gravity. So let me start with the exoplanet, because that's one that we actually talked about in class so far. And the way we really measure the mass of the exoplanet is by looking at the tug of the exoplanet on the star. Remember, it's this balancing act between, it's this cosmic teeter-totter, cosmic seesaw, that as the planet orbits around the sun, the star is having to balance the mass of that planet. And so the star itself is also undergoing an orbit. And we measure that orbit via the radial velocity method as the star wobbles towards us and wobbles away from us, and we can measure that Doppler motion. And that motion that we measure, if you remember from the tablet capture problems that we did, tells us something. That motion tells us something about the period of the planet's orbit, which tells us how far away it is, but it also tells us something about the mass of the planet. It actually directly tells us about the mass of the planet. That is, if we know the mass of the star, which was the first part of the question. And so how we measure, so that's how you get the exoplanets, is via the radial velocity method. That's a direct measure of the mass, but it requires that we know the mass of the star. And so the way we do that is by actually measuring using what are called eclipsing binary stars. Is the way we actually do this. And these are two stars that are orbiting each other. They're binaries, and they actually eclipse each other. And that actually gives us a measure of, by the motions of those two stars, give us a measure of their mass. By looking at their detailed orbits, we actually get a direct measure of how massive they are to produce the motions that we see. And then actually the fact that they eclipse gives us their size. And so both of those things combined allow us to get the direct sizes and masses of stars. And if we do that for a wide variety of different types of stars, like all up and down the main sequence, we can actually then, at a given temperature star, know what the mass and the radius of that type of star is. And then that, of course, is very key to the study of exoplanets, because it allows us to get the masses of exoplanets, if we know the masses of stars, via the radial velocity method, but also allows us to know the sizes of the stars, which are vital to getting the sizes of exoplanets via the transit method. Because remember, the transit method gives us the size of the star, planet, sorry, relative to the size of the star. So you also need to know the size of the star. So these eclipsing binary systems are kind of these magic, really wonderful systems for calibrating those systems. I need to step off for 1 second and grab a power plug. So I'm going to pass to Brandon, or else we're going to be in trouble. Perfect. I'm back, and the juice is in. Ta-da! All right, we're charging again. Okay, next. That's it? No questions? Okay, Leanne has a question. Is there no one else? Oh, sweet, awesome. Hi. Please ask questions.
In the case of the binary system, do we expect a distinct habitable zone like we would for a single star system?
Oh, so Leanne asked, in the case of exoplanets orbiting around binary stars, do we expect a distinct habitable zone? The answer is probably yes. For most of the systems that we have found planets around, and that's because you have two stars that are relatively close to each other, that are kind of in orbit around each other, and then a planet that is called a circumbinary planet, and it's orbiting this binary star. And so the energy that this planet sees is pretty constant. It's coming from both these stars. You can imagine a scenario where maybe once in a while the stars are going to eclipse each other or block each other, where you get a little less light once in a while, but most of the time this planet is going to see the same light from all of these stars and get the same energy. So there's going to be some habitable zone that's based on, instead of just one of the stars' light, based on both of their lights. So yeah, there probably is the habitable zone, but it's based now on two stars' light than one star.
Is that different for the planets that are orbiting one of the stars, and then the entire system is orbiting the other?
So like the really distant ones.
Yeah.
So she said, Leanne asked a follow-up question that was, is that the same as if, again, I told you there was a case if I have two stars that are separated, like, here's my fingers, and I had a planet orbiting this star, and then there's another star way over here. most of the time, this star is so far away in the cases that we've seen that it's not contributing almost any light or energy to this star. That it would be a bright star in the sky, but that's about it. It
Distance
would
order of magnitude?
anywhere from 100 to 10,000 AU.
I wasn't expecting that. Okay.
So even if you put the sun at 100 AU away, it would be a really bright star in the sky, but it would not contribute much energy, much heat to us here on Earth. It would be bright star in the sky, but that's about it. And so most of those systems that the energy wouldn't really be much. That's it.
We don't got a question now.
Okay. If you're online watching, please feel free to ask a question. You can do so in the Google chat, right?
Google Hangout.
In the Google Hangout or on the YouTube links. Feel free to just chat and write in any question you have. Anything is fair game. We'll do our best to answer it.
Alright, so if you have, or was it just figure 8 orbit?
Ooh.
Systems, how far apart they have to be such that that doesn't happen to them.
So I don't know the exact answer. Brandon just asked a really cool question. He said, imagine if you have, two stars like this, and you have a planet that actually does a figure 8 kind of between the two. In fact, maybe I'll go to the board.
This is stable orbit.
It is actually a stable orbit. But I don't know the detailed answer to it. So let me see, I'll make sure you can see this. I have a star here. Yeah, you can see that, cool. And a star here. Yeah, nice. We could get planets that go all the way around here like this. Yep, you can see that. You could get planets that orbit like this. That was the one Ian was just asking about. But you could also have a stable orbit that looks something like that. And Brandon asked how far apart I think that has to be stable
To be in a
or to be in the habitable zone. And my guess is it's something like, it's got to be, we could probably think about this, right? If it were 1 AU, it would be too hot. So it would have to be separated by a little bit more than you would want this point. This point is the balance point here. Oh, wait a second. So it's 1 AU here, 1 AU here, but here it's too hot. So it's probably a little farther than 1 AU. My guess is. I don't know the answer. This is Brandon's asked a very challenging question that probably requires, a detailed simulation and model to fully answer. And the point is that, if I have a planet that's over here, we know that, and these are all, let's pretend these are stars like the sun. A planet here, of course, is going to be at 1 AU, would be in the habitable zone around this star. And same with, that planet when it's in its orbit here. But of course, when it's in between the two stars, it's now getting light from this side, and it's getting light from this side. And so it's getting double the amount of light. And so it's probably too hot if this distance is 1 AU from each star. And so probably there's some balance point where you want it to be a little bit farther away. Oh, there it gets closer. Oh, no. But actually, that's probably fine, because then it spends time over here to cool off. So my guess is actually it's something, a little over 1 astronomical unit. And I have no intuition for how much more that is, but my guess is it needs to be a little bit farther away to dissipate the heat to keep it cool enough to keep liquid water on the surface. And then it goes through this kind of heating mode. But you can imagine that would be kind of cool. You'd be in you actually would have seasonal variation based on where you are in the orbit, which is different than what we have here on Earth, where our seasons are mostly controlled by our tilt. And when we're tilted facing the sun, we're in summer. So in the northern hemisphere, that's, you know, in the months of things like June, where we actually are directly facing the sun in the northern hemisphere, whereas now we're in December in the northern hemisphere, and we're kind of tilted away from the sun, and so it's cold. In fact, it's very cold here in Boston today. We had even snow yesterday here in Boston. And you can imagine from this diagram, you would have very cold winters as you were in these outer parts of the orbit. And as you came to this inner part of the orbit, you'd have very hot summers because you'd be getting the light from two suns shining on you at a very close distance. That's a neat. Did you just think of that? That's cool. Brandon's wicked smart, as we say here in Boston. Cool. Other questions? I hope all of you guys followed some of the links that I sent this week about the Orion launch. There's a really cool video on YouTube that you should check out if you haven't already, just showing the launch of the Orion spacecraft. It's really neat to watch things launch if you haven't seen that before, and that's a really cool thing. The other thing that happened that I'll probably mention in my email that will go out on Friday for the launch of Module 8, but I'll say it in office hours now since we're waiting on questions, is the New Horizons spacecraft woke up this week. And the New Horizons spacecraft is a spacecraft that's on its way to Pluto. It will be the first mission to come near the now dwarf planet Pluto. And it was actually a mission that was called Pluto Express when it launched. And it actually launched just before Pluto was formally turned from a planet to a dwarf planet. And after it was turned into a dwarf planet, they decided to change the mission from Pluto Express, which is supposed to visit the 9th planet of the solar system. And of course, it's no longer a planet, so it's not going to do that. It's now called New Horizons, and it's going to both visit Pluto and then actually some of its neighbors in what's called the Kuiper Belt, which is the region and the collection of objects of which Pluto is just one, which is one of the main reasons, of course, why Pluto was changed from a planet to a dwarf planet, is that it is one among literally thousands of objects out in the far reaches of the solar system. And there's a new spacecraft that is on its way there. It woke up and it took an image, a really kind of nice image of Neptune and Neptune's satellite Triton that you can find on the net. And I'll probably send a link to that on Friday as part of the launch email.
We've been talking about Lagrange orbits in my TPG class, and I was wondering what arrangement the triple star systems have. Are they usually just three in a circle around the common center of mass?
So Leanne asked a question about, she's been talking about stable orbits in one of her physics classes, or in one of her math classes, and that she asked what's the common configuration for a triple star system. Turns out that actually it's very unstable to have the three stars kind of equally spread out. That's a very unstable orbit. What's the most stable is, and what we see most of the time, is to have two that are really close to each other and one that is farther away. And so we call that a hierarchical triple, in that it almost looks like two. It almost acts like two stars kind of orbiting each other like this. Just turns out this one is orbiting itself. That's the most common triple that we see, and it turns out that's extremely gravitationally stable. And it turns out we think that one of the ways that these form is they actually form when they're closer together, and actually as this binary actually gets closer to each other, and as it does, it sheds some of its, or it gains some of its angular momentum, And so the system has to lose angular momentum by this star going farther away. And so we think that those systems form, one of the ways that those form is actually through this kind of interaction that exchanges angular momentum. So that's the most common way that we see them.
Are they usually main sequence stars, all three, or?
The question was, are all that Leanne has a follow-up? Are all three of those stars when we see them always main sequence stars? The answer is no. The answer is most of the time yes, only because the lifetimes of main sequence stars, typically, especially if you're looking at lower mass main sequence stars, are so long that like any triple system you see is just more likely to be made of main sequence stars. But that's not entirely true. Some we rarely see giants in them, just because the giant phase is actually relatively short-lived. But we often see white dwarfs in those systems. So a star that has ended its life and is now a white dwarf, and white dwarfs live essentially forever. Once it's the remnant of a stellar core that literally just cools forever. So they start very hot. Some of the white dwarfs can be, close to 20,000 Kelvin, and then they cool very slowly over time. And so if you see a cooler white dwarf, you're actually seeing a white dwarf that is older, that has been around longer and has had time to cool off. But they cool really to oblivion. As they cool, they also get much dimmer. So it's very hard to observe cold white dwarfs because their brightness actually mathematically goes with temperature to the 4th power. So if they get, twice as cold, then they get 16 times fainter. So that makes them much, much harder to see as they're colder. But yeah, once in a while we do see them. We see white dwarfs. And actually those can be very useful. One of the things that I do in my research group, one of my grad students is working on a project using white dwarfs as, we call them stellar chronometers, or stellar timepieces, or stellar watches. Because we know the physics of how white dwarfs cool. And we know something about the physics of stars that were turned into white dwarfs. So we know something about how long it takes those types of stars to live. So by measuring how long it's taken for a white dwarf to cool, together with how long the star was before it was a white dwarf, you can actually measure its age. And why that's cool is that if the star is in, say, even a binary system, we can make the assumption that that system was born at the same time and from the same material. We can get the age from the white dwarf, and we can apply that to the other star. And the ages of stars are extremely hard to measure. And so that allows us a kind of trick to measure the ages of lots of different types of stars. So that's one thing that we're doing in my research group here at Boston University.
Drake after the guy from the Drake equation, or Drake after the singer?
No, Drake after Drake equation.
What did you do besides the Drake equation?
It's the radio astronomy. Yeah. He also did lots of other side stuff, but he did some traditional radio astronomy.
I never heard of him in any of my context.
Yeah, that's his big claim to fame. It's a pretty good one. Well,
Other people.
any other questions? We still have 15 minutes left in the session. I'm happy to just ramble or get more questions from my two friends who are sitting here. But I would love your inputs from those of you who are watching live. Excellent. Leanne's going to look up some questions for me. One of the things that I typically do in the traditional version of Alien Worlds, which of course I'm teaching actually this semester at Boston University. Today was the very last class actually for Alien Worlds, and we have our final exam next week. One of the days I typically do that I really didn't have time to do much in the MOOC version of Alien Worlds was talk more about my research area. And you already just heard a little bit of some of the research that my group is doing here at BU. But one of the reasons I was excited about, especially when we started talking about other stars in the galaxy, was that in the module that most of you probably are working on right now, is most of my research is actually focused on other stars, and some of that is really talking about the specifics of stellar astrophysics. Some is talking about stars as as members of a larger galaxy, and so I do some galactic astronomy with them. And some of them is some of the science that we do is talking about stars as hosts of exoplanets. So, what are the properties of the stars? How do they affect orbiting exoplanets? So one of the things that I am an expert in, and people in my group are probably even more expert in now than I am, are studying what's called the magnetic activity, which we talked a little bit about in the MOOC. But the fact that these stars have flares and give off high energy radiation, we think that that might actually be something that affects how habitable a exoplanet is when it's in orbit around some of these stars. And so we try to characterize that in types of stars and learn how that changes as a function of type of star, as a function of the age of star, as a function of where you find these stars in the galaxy, which we think will help inform us both in identifying new exoplanets that could be potential habitable worlds, but also assessing the true habitability of exoplanets for many of the worlds that we already know. So that's some of the stuff that I think about when I have time, which is not very often right now, because I'm spending a lot of time teaching traditional Alien Worlds, and of course putting this massive open online class together. Any other?
Can you explain to me technically how Kepler was able to stay pointing at one point in space the entire time it was in operation?
I think so. Leanne's question. One of the things that it used to do, it doesn't do this anymore for some reasons that it broke a little bit, but not enough to fully break. Was that one of the things it did is it pointed really in the same patch of the sky and really stared at that for years. It actually did some rotations and things like that, but it would stay very fixed at the same part of the sky in very precise fashion. I think the way it did that is actually using gyroscopes.
Yeah.
Isn't that true? Oh, is it reaction wheels? Or those?
They were full reaction wheels.
But aren't those gyroscopic motion?
No, I think they spin, and the angle of them spin can cause the ship to move.
Oh, well there you go. So Brandon knew the answer and I didn't. See?
They might have had gyroscopes.
No. I think you're exactly right. So they have what are called reaction wheels on board that spin, and they actually the spinning of the wheels they spin them at the right rate so that
I think they're not perfectly spherical. They're like oval shape in that they don't have the rotation axis through the center, so that when you spin it, you like get a transfer of angular momentum.
Oh. And so you can actually make small corrections or account for your orbital motion by.
Yeah, it's exactly like what vibrates your phone. They have a little non-center thing that just spins and vibrates your phone. But it's the same processes.
Interesting.
I didn't know that either.
Interesting. So Brandon's saying that they're on board the spacecraft are these wheels that are in motion, and they're not perfectly symmetric, such that as they rotate, they generate angular momentum that can actually alter the spacecraft's pointing, if you will, and they can spin, I assume, at certain rates and then transfer very precise amounts of angular momentum to make corrections to the pointing at a very precise level. Does that sound
I think so.
pretty right?
I know they have 4, and then they need 3.
You need 3, that's right. So the spacecraft had 4 of these. You need 3 to control an axis, pointing axis this way, pointing axis this way, and then pointing axis this way. So those 3 directions you would need to be able to control the spacecraft. 2 of those, I think, broke. So they only have 2 now. And so there's one axis that they cannot control as precisely. And so they no longer can point Kepler towards the traditional Kepler field, but they've actually done some trickery. And they can actually point at some other fields by using, I believe, some of the orbital motion, maybe even the sun. If I remember correctly, they can use like some sun pressure and the orbital motion of the spacecraft to point to other.
Yeah, I think they're using 2 reaction wheels and the radiation pressure from the sun.
Right. Right. So they have 2 reaction wheels, and then the radiation from the pressure from the sun keeps the other axis fixed. And so there's certain places they can point at certain times of the year, depending where Kepler is in its orbit, so that the sun's pressure hits a certain side of the spacecraft. And so Kepler is now beginning to point at totally new fields, and NASA has had calls to allow scientists to propose to observe specific targets in those fields. So I'm actually awaiting NASA telling me whether or not I get to observe a certain number of targets in one of those fields. So I put in a proposal, I don't know, several months ago to observe several hundred targets, actually of binary stars, in 2 of the Kepler fields, the new Kepler fields. And we're waiting to see if those were selected.
How do you go about picking hundreds of targets? Do you go through them one by one, or is it an algorithm?
Yeah, so Leanne asked, how do you go about picking targets, and especially when there's hundreds of them? We write computer code to go through. Actually, we started with many tens of thousands, if not hundreds of thousands, of candidate stars that are in those 2 new fields. And we had certain criteria, which for us, the main thing is we wanted to ensure that high probability that the 2 stars were really associated with each other and could both be observed by Kepler. And so that about a few hundred. Other questions, comments? Nothing?
There was one person who was asking a lot of questions and didn't specifically answer.
Okay. Well, I'll see if I give the same answer.
He wondered if there was any way for planetary systems in a galaxy to have a preferred alignment. Specifically, he thought that these particular planetary systems should always be
Uh-huh.
perpendicular to the galactic.
Got it. So there was a question in the discussion forums about whether or not planets do and or should have preferred orientation. Planetary systems should have a preferred orientation in relation to the galaxy. I guess one might think that that might be possible since the galaxy is this rotating at a pretty fast speed. All of our evidence so far from the planetary systems we know, which includes our own, is that there does not appear to be a preferred orientation, that it appears to be pretty random. Certainly our own planetary system, the orbit, the disk of the planet, or the plane of the planet's orbits, is offset from the galaxy. It's neither perpendicular nor parallel to the galaxy. It is offset by a significant angle. And that seems to be true of all of the planetary systems that we see, where we can actually measure this, at least measure the planets' orbits and figure out their kind of alignment, if you will. It appears to be fairly random. Again, as stars are forming, they're forming from a big ball of gas and dust. And although that gas and dust is a part of the galaxy and is rotating with the galaxy, a lot of the small-scale physics that kind of starts this process in motion really doesn't pay attention to the larger galaxy. It doesn't know anything really about the motion of the galaxy. You have things like magnetic fields and small pockets of your cloud that are maybe going to be a little more dense and so have a little more gravity. Where those occur is what is going to help start the cloud having a little bit of preferred rotation or motion. And as the cloud collapses, that motion is going to be enhanced as angular momentum is conserved, just like as the ice skater moves his or her arms in, the star and its system speeds up. That's going to happen at a preferred or at a direction based on those initial really, really tiny motions, which again are based on very small level physics that really doesn't know anything about the larger galaxy. And so we see no evidence of that yet. Now, as I tell my traditional Alien Worlds class, science changes. And who knows, when we look at even more exoplanets, we might find evidence that that's not true. But our current evidence, including, again, our own solar system, is that there doesn't appear to be a preferred orientation for planets and their orbits. Is that consistent? Okay, good. It's good we don't contradict each other too much, at least.
Well, we're approaching 58
Well,
minutes.
we are approaching the witching hour. That is the end of office hour number 3. Are there any last questions from those of you? I still see there's a few of you online watching us. Any final questions that you might have before we check off? Any questions about the course, astronomy, planets, anything?
The final.
The final?
Would be a good time for that.
Yeah, there's going to be a final exam, of course, in this class, or a final assessment project that will be released next Friday with the final module. There'll be a short assessment associated with Module 9, which is the final module, which will release next Friday, not Friday in a few days, but the Friday after that. We will release the final assessment along with that final module, and it will be cumulative. It'll be an assessment that tests you on kind of the basic, but most important principles from the entire 9 modules. And we'll probably do, what do we say, 2 or 3 questions per module.
I think there is room for ones that I think are good candidates.
Excellent. And Leanne is helping put that together so that we will finish that in the next week. Excellent. All right. Well, I think we'll end that there if there aren't any other questions. Certainly for those of you who are watching now and those of you who watch later when this gets posted to YouTube, we will have one more of these office hours next week, next Wednesday, perhaps. And so I highly, it's not Monday, I sure hope, because I'm out of town.
It's Tuesday.
Good. It's Tuesday. Oh, next Tuesday. Great. What time?
1 to 2?
1 to 2, at least.
I next Wednesday.
I have next Wednesday too. I think on my calendar. Good. Okay.
Thomas will go, so.
Wednesday the 17th. At 1 to 2.
Oh,
Yeah.
great. Then I'll be able to
At
come.
1 to 2 Eastern time. So that's 6 p.m. or 1800 Greenwich time for those who are counting and not on the Eastern Standard Time zone like us here in cold Boston. So I really encourage you to attend the final office hour if you can, and if you can't, please post questions to the thread that Brandon will put up on the discussion forum so we can have a lot more questions for our final Alien Worlds office hours. So have fun, and I'll talk to some of you next week. Take care.